So far, all of the Lewis structures we've drawn have obeyed the octet rule, and most of the time that's true. However, in chemistry there are always exceptions, and so right now we're going to discuss a few exceptions to the octet rule. Some of these happen just because of how many electrons you have. So exception number 1 here, odd electron species, also called free radicals. This simply occurs when you add up your valence electrons and you get an odd number. If you have an odd number of valence electrons, there's just no way to give everyone an octet. What you can do, however, is you can figure out the lowest energy structure by looking at formal charge. So you can get it as good as it can be, even if it can't have an octet. The second exception is an incomplete octet. And really, the only element we have to worry about who does this is boron. Boron prefers to have 3 bonds instead of 4 bonds, and he does that because of formal charges. So formal charge leads to this exception to the octet rule. Last one are expanded octets. This is one where instead of having fewer than 8 electrons, an atom will actually see more than 8 electrons, 12 electrons maximum. Only elements in the 3rd row of the periodic table and below are allowed to do this because they have some nearby d orbitals that they can use to accommodate those extra electrons. Atoms in the 2nd row and above don't have those nearby d orbitals, and therefore they're not allowed to do this. Sometimes it's really obvious to see this because the element will be bonded to 6 things, so it just has to have more than 4 bonds. But sometimes it actually will do this just to lower its formal charge. That one's a little less obvious, so we'll look at examples for both. So let's practice a few of these. First one, let's just write the Lewis structure for each molecule. Get out my pen. So let's start with NO. So we'll do what we always do. We'll add up my my valence electrons. So nitrogen has 5, oxygen has 6. So I end up with 11. So I can see right away, not going to be able to get an octet here. Odd number of electrons, it's just not going to work. So we'll do what we can. I have my nitrogen and oxygen. So I used up 2, so I have 9 left. Since oxygen is more electronegative, I'm going to give him his electrons first. So I'll do 2, 4, 6, 8, 9. Ugh, that looks ugly. That's all we can do. We can at least get things as good as possible. Nitrogen can't have his octet, but right now he only sees 2, 4, 5 electrons. We can at least get him close. Or we can also calculate formal charge to see how we could make this better. So if we calculate formal charge, nitrogen has 5 valence electrons, and here he has 3 dots and 1 line, so he's positive 1. Oxygen has 6 valence electrons, here he has 6 dots and 1 line, so he's negative 1. So they add up to 0, but we could probably make this better by getting the formal charges to actually be 0. Nitrogen wants to see more electrons, and oxygen wants to see fewer electrons. So what we'll do is we'll make oxygen share. So now we have a double bond. So if we recalculate nitrogen's formal charge, he has 5 valence electrons usually, but now he has 3 dots and 2 lines, so that's going to make him 0. For oxygen, he has 6 valence electrons, and here he has 4 dots and 2 lines, so he is 0. So this is going to be the best possible Lewis structure we can draw. Nitrogen doesn't have an octet, but he does have a formal charge of 0, so he can at least be satisfied in that way. All right, that's our first example. Now let's look at, there we go, BCl3. Same thing as always, valence electrons first, so boron has 3, and then we have 3 chlorines, each of which has 7, so that's going to be 24 total. So we'll put boron in the middle. He's the least electronegative, so he's going to go in the middle. Put 3 chlorines around him, so I've used up 6, got 18 left. 2, 4, 6, 8, 12, 14. Wow, I can't count. 2, 4, 6, 8, 10, 12, 14, 16, 18. Whew, that was bad. Okay, so I've given all of them away. Normally, we would look at boron and say, okay, he's unsatisfied. We're going to make a double bond. But this is just an exception we have to remember. Boron is perfectly happy right now. He's not going to form a double bond. And the reason, again, is formal charge. If we look at boron, boron has 3 valence electrons, and here's no dots and 3 lines, so his formal charge is 0. If we force him to take a double bond, it will change his formal charge and he won't be 0 anymore. So we're just done. We don't have to make a double bond, nothing like that. So we just need to remember that boron likes to only have 3 bonds, not 4. Alright, next we have krypton dichloride. So same thing we'll always do. Krypton is a noble gas, so he actually has 8 valence. And now I have 2 chlorines, each of which has 7. So that's 14 plus 8, 22. Krypton is less electronegative, so he'll go in the center. I'll put chlorines around there. And then I used up 4 to make bonds, so I have 18 left. 2, 4, 6, 8, 10, 12, 14, 16. And we say, okay, I gave them all an octet, but I have 2 left. I've got to put those electrons somewhere. They can't just disappear into the ether. They got to go somewhere. So I'm just going to stick them on krypton. And done. That's it. I know it looks a little weird. We don't really like it, but krypton's okay with it because, again, we count as formal charge. Krypton has 8 valence electrons. Right now he has 6 dots and 2 lines. His formal charge is 0. He's perfectly happy to accommodate those 2 extra electrons. And because he's below the 3rd row of the periodic table, he's allowed to do that. So if you end up with extra electrons at the end, you just got to throw them on. They got to go somewhere, so just put them on the central atom. All right, last example. Let's look at PO4 3- here. He's a little big, so we're going to go to the next page for this one. So we've got PO4 3-, our phosphate ion. And of course, we'll start with what we always do. Phosphorus has 5 valence. I have 6 oxygens, each of which has 4. And then because I have a -3 charge, I need to put in 3 more here. So 6, 20, 24, plus 5 gives me 29, plus 3 gives me 32 valence electrons. Phosphorus is the least electronegative, so it'll go in the center. And I'll put some oxygens around here. Okay, so I've used up 8. So I've got 24 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used them all up. Because he's an ion, we bracket him. Normally I would say we're done. But if you look back up, which I can't do right now because I'm drawing all over it, it said specifically expand the octet if necessary to lower formal charge. When I see that instruction, it pretty much tells me I'm going to have to break my octet. So what I need to do is calculate the formal charge on phosphorus to see how I can make him happier. So phosphorus here, if we calculate his formal charge, phosphorus normally has 5 valence electrons. Here he has 0 dots in him, but he has 4 lines, so he has a formal charge of +1 right now. So he would like another electron. So in order to lower his formal charge, I can make one of these oxygens share more electrons. So I'm just going to arbitrarily pick this guy. Now we can see here's an opportunity to draw resonance structures, but I'm not going to do that. But we can see we would have 4 different resonance structures, 1 for each of the oxygens forming the double bond. So now for phosphorus, 5 valence electrons, -0 dots, -5 lines, his formal charge is 0. So this is another valid Lewis structure because although he breaks the octet rule, he has lowered his formal charge. And I always like to be very explicit. When I want you to do this, I will say, expand the octet if necessary to lower the formal charge. Because it's hard to say between the octet rule and the formal charge which one's really better all the time. There's not a hard and fast rule. So I'll be very explicit in my instructions. But we can see we calculate the formal charge. If it's positive, we just make an extra bond, make a neighbor share in order to get that guy down to 0. And we're done.